Welcome to the lecture on Monte Carlo integration. This is part 1, and we will be going through the basics, do some recap, and look at how we can do some basic sampling and integration according to the Monte Carlo procedure. And today's goal will be to put into practice what we saw last time, and that is the integration of the cosine-weighted incoming radians at a point x. And the integral that we will have to compute is that of the light function over the entire hemisphere with respect to direction or solid angle omega. However, this is easier said than done. Right off the bat, there are two questions that arise. One would be, how do we even integrate over the hemisphere? And the second would be that the light function, that is what we are trying to integrate, depends on light's geometry, is in general quite complex, is not necessarily continuous. In fact, in most cases it isn't. So how can we even integrate something like that? And the solution that we will eventually arrive at is that of Monte Carlo integration, which draws from other fields like statistics, probability, some calculus, which are all combined in order to get to this final procedure. And this is actually a lot to take in because some of the concepts that are involved or implied in Monte Carlo integration can be a bit difficult to grasp and might be a bit complex. So in order to illustrate them and make them as easily understandable as possible, we try to explore them in an illustrative way in these next few lectures, because we believe that once you grasp the underlying ideas, it makes their application much easier and much more sensible. And we will try to present the bare necessities that you need in order to write a renderer yourself for each of the topics that we go over. So the basic takeaways or the basic formulas that you need to remember in order to write a renderer are actually rather easy, but the road to get there is a bit more complex. However, we believe that it is worth the effort so that you can not only apply the formulas and the computations, but also understand what is actually going on under the hood. Before we get to the new topic of Monte Carlo integration, we want to do a detailed fundamentals recap. And we will start off with calculus. We will look at derivatives and integrals. And these are topics that most of you are probably already familiar with, but we will look at them for two reasons. The first is so that we can remind you of the typical notation in the context of derivatives and integrals. And the second is that, as we stated before, we want to explore Monte Carlo integration in an illustrative manner. And for this, we want to have this continuous theme of integration basically being the process of disassembling complex functions into simpler, smaller parts and then reassembling back together. The second large topic that we will look at is probability and statistics. And we will look at discrete and continuous random variables. We will look at uniform and non-uniform distributions. We will look at the probability density function and the cumulative distribution function, and also expected value and variance. First off, we will look at derivatives. And for a function f of x, the derivative f prime of x gives us the rate of change of the function at a particular point x. And the derivative answers the question, how does the function that we're looking at change within an infinitesimally small range dx around x? And the idea of infinitesimally small things is something that we will revisit quite a bit throughout this lecture. We will look at infinitesimally small ranges and intervals, so it's best to get comfortable with this concept right away. The closed form solution for a function's derivative doesn't always exist, which means that just because the function can be expressed in a simple combination of variables and different mathematical operations doesn't mean the same is also true for its derivative. This is particularly the case for discontinuous functions. Functions of multiple variables can be derived with respect to any of the variables, which yields a so-called partial derivative. And a partial derivative is indicated by the special character for partial derivative in front of the variable that we are taking the partial derivative with respect to, instead of the d for the common derivative. Moving on to integrals, we distinguish indefinite integrals and definite integrals. And the basic notation for indefinite integrals is as shown here. We use capital F of x to represent the integral of the function f of x. And the indefinite integral f of x can be any function that fulfills capital F of x prime equals the function f of x, meaning that if we take the derivative of capital F of x, we get f of x as a result. And for this reason, the indefinite integral is also commonly referred to as the antiderivative. By this definition, we can include arbitrary constants in our solutions for the indefinite integral, because those constant values basically fall away as soon as we take the derivative. For the definite integral, we have a similar notation, but we have additional variables for the range that we want to integrate over. So in its full form, for the definite integral, we have the variable of integration x. We have the integration interval a to b, which are basically the values that we're interested in x taking on. We have a function f of x that we want to integrate. This is often referred to as the integrand. And we have the differential dx for x. And informally, we can interpret the definite integral of a particular function as the area under the curve for that function. The differential dx in this case is an infinitesimal range, which makes f of x times dx an infinitesimal area. So the integral in a particular range can be understood as the sum of these small areas in the interval a to b. We can visualize this idea of the definite integral being the sum of infinitesimally small areas by starting off with a range delta x from a to b and multiplying it by f of x at the start of that range. And this will give us a rather coarse approximation of the area under the curve. But as we keep making delta x smaller and smaller, we see that the sum of the areas, f of x times delta x, keeps getting closer and closer to the true result of the area under the curve. If we have a solution for the indefinite integral capital F of x being the antiderivative of the function f of x, we can quickly solve the definite integral in the range a to b by simply subtracting capital F of a from capital F of b. And below we see an example of this in practice, and also to visualize the concept of area under the curve. We have the function of the unit circle, which is x squared plus y squared equals 1. We know that the area of the unit circle is exactly pi. So we can first solve for y, which is square root of 1 minus x squared. And we can then use some sort of mathematical toolbox or platform, in this case Wolfram Alpha, to compute the antiderivative, and then take the value of the definite integral in a particular range, in this case from 0 to 1, by simply computing capital F of 1 minus capital F of 0, which in this case gives exactly pi over 4. In order to generalize to n-dimensional space or an n-dimensional domain, we will be talking about volume rather than area under the curve. And in the case of an integration over multiple variables, which gives us a multidimensional domain, we will be using subscript-only symbols. For instance, the integral over D to represent the integral over an entire domain D. And integrating over 1, just as a reminder, for a given range A to B will give us a result that is equal to the volume of the range. And integrating 1 over an n-dimensional domain will be equal to the volume of that domain. And we also use a special function to represent that value. For instance, for a domain D with different variables x, y, and z in different ranges, we have volume of D represented by the integral over all these different ranges. Next up are random variables, and we indicate random variables with capital letters, for instance x, y, and so on, and some Greek symbols for special random variables. And random variables are always drawn from some domain that defines the possible results that we can get back from a draw from random variables. We define an outcome or event for each draw from a random variable, and we denote an event or an outcome from a random variable with subscripts. So for instance, xi marks an observed particular outcome of a draw from a given random variable x. And random variables can be distinguished in discrete and continuous random variables. The occurrence or the probabilities of these values that we can observe from a random variable usually follow some kind of probability distribution. If a random variable has a uniform distribution, all possible outcomes are equally likely to occur. So for instance, in a fair die or a fair coin. For non-uniform variables, the probability of particular values is much higher than for others. So for instance, if we take the average body height in a population, we are much more likely to see results close to 5, 6, or 7 feet, and 1 feet, 2 feet, or 13 feet, 14 feet are much less likely. First up, we will look at discrete random variables, because those are the ones that we are most often confronted with in daily life. For instance, a coin flip or the toss of a die or cards in a deck are all instances of discrete random variables. Each possible outcome of a random variable is associated with a specific probability, and those probabilities must sum up to 1 or 100% over all the possible outcomes of a random variable. So for instance, in a fair die, here modeled by the discrete random variable x, we have possible values out of the range from numbers 1 to 6, and the possibilities for each of these events, p1 through p6, are all equal to 1/6. In contrast, a continuous random variable can assume any value that falls within a predefined range. So instead of enumerating all the possible outcomes for a continuous random variable, we only have to define its limits. In practice, we are almost always working with some level of discreteness. However, the theoretical concept of the continuous random variable allows us to generalize the main methodology for many evaluations in probability theory. And at least as a theoretical concept, the continuous random variable has infinitely many possible outcomes, and consequently, the observation of any particular event from those infinitely many has vanishing probability. So that raises the question, how can we find probabilities for events in continuous variables? This issue brings us to the concept of the cumulative distribution function, or CDF for short, and the CDF enables us to compute the probability of a random variable taking on any value inside a specific range rather than any specified value itself. We use the notation capital P to indicate a CDF. We use the subscript to indicate which random variable the CDF is connected to. and we use the parameter to answer the question. For instance, in the case of px of x, what is the probability of the random variable capital X taking on any value that is smaller or equal to the parameter lowercase x? And by this definition, we can easily compute the probability of a random variable x taking on any value inside an arbitrary range from a to b by computing px of b minus px of a. And below we see an example. We have a uniform variable in the range from 0 to 1. And for this particular random variable, the CDF is simply the linear correspondence x. And we can quickly confirm that for a given range, we get an adequate result for the probability of a uniform random variable being inside a range from 0.5 to 0.75, which is exactly 25% as expected. There are certain properties of the CDF, certain restrictions that it needs to adhere to. The CDF is bounded by 0 from below and 1 from above, and monotonic increasing. And there are intuitive explanations for both of these restrictions. The probability of no outcome is 0, because if we draw from a random variable, we must get an outcome. And the probability of some outcome occurring is 100%. And regarding the monotonic increasing property, if we look at a die, then rolling a number between 1 and 6 cannot be less probable than rolling a number between 1 and 5. So if we have a set of outcomes and their cumulative probability is some value, then adding an additional event to the set cannot decrease that value. CDFs can be applied for both discrete and continuous variables. And the question now is, how do we compute CDFs for our random variables? For discrete random variables, computing the output of the CDF is quite straightforward. If we have a discrete random variable x with a given limit and associated probabilities for every event in that limit, then we can easily compute the cumulative probability of a given value x by simply summing up all the probabilities of values smaller or equal to x. For continuous random variables, we cannot do the same thing because we cannot enumerate all the possible outcomes of a continuous random variable. This is where the probability density function, or PDF, comes in. And the PDF is the derivative of the CDF. For a given PDF, we can find the CDF by taking the indefinite integral of the PDF. And also, if we need to compute the integral over the PDF for a particular range, then all we have to do is compute the two outputs of the CDF for the lower and upper limit, and then subtract the lower from the higher. The PDF must be positive everywhere, and there's an intuitive reasoning behind that. A negative value in the PDF would mean that we can find a range AB in the CDF such that for that range we get a negative probability, which is impossible. The output of the PDF for a corresponding random variable can be understood as the relative probability of that random variable taking on that value. For instance, if we have the output of the PDF for a given value A that is twice as high as the output of the PDF for another value B, then it means that the associated random variable is twice as likely to take on the value of A than it is to take on the value of B. A few notes about the PDF. Its notation may look like we are referencing probabilities, but the outputs of the PDF can exceed 1. So it's not a classic probability in that sense. However, for both discrete and continuous random variables, this means that we can write P of x to describe the distribution of their output values, even though we're talking about probabilities in one case and the PDF in the other. So in summary, if we have a continuous random variable with a known integrable PDF, we can compute the CDF by taking the integral of the PDF and thereby find a way to compute probabilities of a random variable landing inside given ranges. The question is, how does that help us in the long run to arrive at our goal, Monte Carlo integration? But there is a very practical application for this, because by discovering the CDF, we have found a powerful new tool for creating random variables with custom distributions. And this is due to the fact that the CDF is often invertible, and that means instead of analyzing a random variable and finding its probability density function, we can instead define a desired distribution or probability density function and then compute the corresponding random variable whose outputs will behave accordingly. And the rationale behind this is that since the CDF is monotonic increasing, we can find a unique value of the outputs of the CDF for every input that we take. More informally, if we have a 1D plot of the CDF, then for any x value, we can find a unique value on the y-axis and vice versa. So our first big goal will be to generate samples for custom-made random variables from a distribution, an input distribution that we can easily obtain in a computing environment. And one such distribution that we can easily obtain is from the canonical random variable Xi, which is continuous, meaning that is a real data type in a computing environment. It has uniform distribution, and all its output values are in the range from 0 to 1. Now, our very important first goal will be to take samples of Xi and find a way to warp those samples into new ones that are distributed according to some different desired PDF. A few notes about the canonical random variable. It will be our assumed default input variable, meaning that if we need some other distribution, we will assume that we can always obtain samples from the canonical random variable and then perhaps convert them via some other process into another distribution that we need. The PDF for the canonical random variable is constantly 1 in the range from 0 to 1 and 0 everywhere else, which implies that the CDF of the canonical random variable is linear, and that yields an important property, namely that the output of the CDF from a sample drawn from the canonical random variable is equal to the input. And we can exploit this property in order to achieve what we wanted to do before, namely to simulate a random variable with a given PDF/CDF. And the way to do that is by using a process called the inversion method. If we have a random variable x with some distribution, we can draw a sample from our canonical random variable Xi and consider it as the output of x's CDF to find the value of x that would have generated it. In the discrete case, we can simply iterate over the outcome probabilities of x and stop at the event where their sum surpasses our sample of Xi. For the continuous case, we can use the bijectivity of the CDF and take its inverse. So the value of random variable x that would have produced the cumulative probability given by our sample Xi is found via the inverse of x's CDF. And as a first small example, we will look at the exponential distribution and we will try to simulate it with the canonical random variable as input. Now, the exponential distribution is used mainly for the estimation of time intervals between two events. The probability of observing a particular value decreases exponentially. And there's also an additional parameter lambda that is often called the rate parameter. And we can find the defined PDF and CDF for the exponential distribution in most probability textbooks. Its PDF is lambda times e to the power of negative lambda times x, and its CDF is 1 minus e to the power of negative lambda times x. So what we are doing here is we are basically putting into practice what we just saw. We are computing the inverse of the CDF and thereby simulating an exponential distribution by warping the outputs of a uniform distribution. And in order to evaluate this, we are going to write a simple C++ program that uses two different random variables. One is using a uniform distribution and one is using an exponential distribution. And what we are trying to do here is we are recording all the samples that we draw from the variable created with an exponential distribution. We are also recording all the samples that we generate from the uniform distribution. And last but not least, we are recording the warped samples that we obtain by taking the uniform samples and applying the inverse function of the CDF for the exponential distribution here. So in order to evaluate how well our warping method performs, we have plotted here histograms of the values that we get out of the different random variables that we have created. We have in the upper right-hand corner our reference, that is a variable that was created with an exponential distribution by the C++ standard library. We have on the left-hand side the samples and the histogram of all the values that are generated by samples from the uniform input distribution Xi. And we have on the right lower the outputs that are generated by our warped random variable from the uniform inputs. And as you can see, there is very little difference in terms of the behavior between the reference value that was created from the library with an exponential distribution and our warped samples from the uniform distribution as an input. So apparently the results are very similar between the reference and the warped solution for the exponential distribution. But if you do a little digging into the source code of the standard library, this will not come as a surprise, because what we have written down there is actually exactly how the exponential distribution is implemented in the standard library anyway. So it's good to know that this is actually an accepted reference solution. So now that we saw that we can simulate individual random variables from their PDFs, let's move on to two-dimensional space. We can generate some basic 2D distributions by combining the output of two random variables. By doing so, we are extending our sampling domain. When we talk about multidimensional sampling, the domain defines the number of random variables we are using and their respective range. For the sake of visualization, we will plot the domain as a space where the axes represent the individual random variables. In a domain with multiple random variables, every possible outcome is a combination of the values that the random variables can take on. Therefore, we define the joint PDF for any such combination that defines a point in the shared domain. In the simplest case, we have independent variables x and y, and if they are independent, then the joint PDF for a point in their shared domain is simply the product of the separate PDFs for each coordinate separately. In this case, we can simulate a 2D random variable by computing the inverse of the individual CDFs and using the inversion method on them with outputs from two canonical random variables. Here we see an example of that where we use a random variable for the y-axis that mimics the canonical random variable and another random variable for the x-axis where the probability is distributed according to the cosine of x. Since the cosine is 1 for input 0 and 0 for input pi over 2, we can see that the density of the samples decreases with increasing x. The sampling of this 2D variable is achieved by inverting the individual CDFs separately and warping samples from two canonical random variables as shown in the code below. Here we have another small example with variables x and y, both in the range from 0 to 1, and for both variables we are using the same linear PDF. Again, we can sample this distribution by computing the CDFs, inverting them, and using samples from different canonical random variables as input. It may be difficult to tell visually, but the joint PDF tells us that there are approximately 4 times as many samples in the upper right corner than there are at the center of the plot. So let's try a little variation on the last setup, and instead of having variables in the range from 0 to 1, we actually want them to replicate the behavior of a linear PDF in the range from 2 to 4. And this means that we would see a smaller change in the density because the relative growth of the function in that range is smaller. So if we go and apply the same recipe as before with a different range, then nothing happens. If we plot a higher range, then we see that the samples are the same as before, which is no surprise because our CDF and inverse CDF are also identical to the ones that we got before. So apparently we are missing some crucial steps if we want to apply the inversion method to arbitrary setups with arbitrary ranges. So let's look at the missing steps right away. First, what we need to do is ensure that we enforce the necessary restrictions on the PDF and CDF we are using. For now, let's talk about the distribution we want our variable to have as the PDF candidate f of x. Remember that we said that a CDF is bounded from above by 1. That means that if we have a random variable with a specified range, the integral of the PDF over that range must equal to 1. If this is not the case, it corresponds to saying that the probability of the variable's outcome being one of all possible outcomes is not 100%, which is a paradox. To fix this, we can compute the proportionality constant by finding the value that f of x integrates to over the full range and divide f of x antiderivative by it to get a valid CDF. This ensures that the CDF adheres to its necessary restrictions while making the PDF p of x proportional to the candidate function f of x. Furthermore, if we are looking at ranges that do not start with 0, we also need to add a constant offset to the CDF. If our variable ranges from a to b, then we subtract the value that the CDF would produce for input a. This is valid because we defined the CDF to be the PDF's antiderivative, and remember that antiderivatives can include arbitrary constant factors because those fall away when we differentiate. With this in mind, we try our setup from before again, but this time apply the proportionality constant and the correct offset. And as we can see in the updated plot, this now produces samples with the expected growth in density and in the expected range. So finally, we have the inversion method for simulating random variables with custom distributions completed. To summarize, let's go over the individual steps we need to do once more. First, we identify a candidate function f of x that we want for the distribution of values in our random variable. Second, we choose the range inside the candidate function that our variable's distribution should imitate. We then compute the indefinite integral or antiderivative of the candidate PDF to get a candidate CDF. We find the proportionality constant and the final CDF by subtracting the offset and dividing by c. We then invert the CDF, and from now on we can use the inverse to compute warped samples with the desired distribution by using samples from the canonical random variable as input. So let's take a step back for a moment and look at the PDF from a different angle. We saw 2D samples being warped into a new 2D distribution, and we can interpret this warping as a transformation of the space from the input domain to a target distribution. If we convert uniformly spaced input samples with the inversion method, as we saw, we usually don't get uniformly spaced outputs. So let's treat some tiny regular interval in the input domain as an infinitesimal hypercube. A hypercube is a line in 1D, a square in 2D, and a cube in 3D. And if we warp the inputs of canonic variables, as we did before, to samples of a distribution with a joint PDF PD, then we can express the change in the volume of these hypercubes by 1 over PD. Let's take a look at an example with a single custom random variable. This random variable x has a PDF that equals 2 times the input coordinate x, which means, for example, the volume of the infinitesimal hypercubes that we mentioned before at coordinate x equals 1 is half of those at coordinate x equals 0.5. And we can quickly confirm this by checking the change in length of some very short line segments when they are transformed from their uniform space to the one modeled by the custom distribution and mathematically confirm this. But it's a bit difficult to get an intuitive understanding of what we want to express by the transformation with the PDF this way. So let's look at some more 2D examples. Here we have on the left our input variables xi1 and xi2, and we plot a regular grid over the entire 2D input domain. On the right hand side we will plot the same grid coordinates after we warp them with the inversion method to produce the distribution given below, which is uniform for y coordinates and linear for x coordinates. And we can see that if we do that, the areas of all 2D hypercubes are scaled by a factor of 1 over px of x. Note that after the transformation, the rectangles on the very right are approximately half as wide as the original ones because there x equals 1 and we have a scaling factor of 1 over 2 as compared to the original size. Now remember that just before we saw samples for random variables x and y, where we had px of x is 2x and py of y is 2y, so a linear PDF for both the x and y random variable. Now, because it is a two-dimensional setup, we have a joint PDF p of x and y. And in this case, because the random variables are independent, we have p of x and y is equal to px of x times py of y, given 4xy. And we can see that the areas near point 1, 1 in the coordinate system are squished to 1/4 compared to the original squares after the transformation. Again, we can see that 1 over the PDF gives us an indication of how much space is transformed if we move from a uniform input to a random variable with a particular PDF. And if we plot, once again, the samples that are generated by the canonical random input variables, and again after the transformation to a distribution with a different desired PDF, we can see that the space that was occupied before by a small hypercube has now been expanded, and with it the distance between the samples in this region. So in summary, an alternative way to interpret the PDF is to take a look at its reciprocal and treat the resulting 1 over the PDF as the change of the volume for infinitesimally small regions, areas, or volumes of hypercubes at given points. The last topic of our introduction to the fundamentals for Monte Carlo integration is statistics. And the main concepts that we need to cover here are the expected value and the variance. So for a short recap, let's start with the expected value. The expected value, denoted by capital E, of a continuous random variable with a given distribution is computed as the integral of all possible values x over the entire domain or range that the variable covers times the corresponding output of the probability density function. In the discrete case, we would be computing the sum of the products of all values of x times the probability of seeing each specific value. So with this definition, we can describe the expected value as a form of weighted average over all the values that x can produce. To sum up, the expected value basically answers the question, what is the average value that we can expect to draw from x? And it should be noted that there is an emphasis on average here, because it is possible that the expected value of a random variable is one that it actually never outputs. For instance, if the values it produces are either very high or very low, then the expected value could be something in between. So basically a value that is never generated by x. Moving on, we come to the variance, which for random variables can be defined as the expected squared deviation from a mean that we get by computing the expected value of variables. In other words, the variance for a variable x is the expected value for the subtraction x minus the expected value of x squared. In combination, the expected value and the variance work together to describe a random variable adequately. The expected value gives us the expected mean, and the variance tells us how much the actual outputs of the variable fluctuate around that mean. So in the case that we mentioned earlier, where the expected value is somewhere in between the values that a variable produces, we would see a relatively high variance. Note that for both the expected value and the variance, the PDF that we use for computing them is actually part of the notation. So with refreshed knowledge of calculus, random variables, CDFs and PDFs and statistics, we have all the tools in order to approach Monte Carlo integration as a new topic. And you're going to try to do this in an explorative manner, since historically integration has developed as a tool for approximating the area under a complex curve by means of increasing accuracy through splitting and subdividing complex structures into ever smaller basic shapes and then reassembling them back together again. And we're going to try to do the same thing and arrive at an intuitive solution that leads us to the practice of Monte Carlo integration in order to compute an accurate integral for a given function. Before we dive into this, let's just quickly clarify why we even have to consider Monte Carlo integration in the first place. In many situations, we cannot find a closed form solution for the integral of a function. Monte Carlo integration shines specifically in cases where we cannot compute the integral of a function analytically. So in the best case scenario, we might have a basic idea of what the function we are integrating looks like, but the exact shape is not known to us. The light function in rendering is a particular example of this. The light that is coming in at a point can be influenced by the entire scene geometry. Hard shadows make the light function discontinuous, and we haven't even started yet with the rendering equation, which contains an infinite dimensional integral. So there are plenty of reasons for us to look for solutions that give a good approximation in the absence of an analytical solution. One way to find the area under a curve is by sampling the integrand function f of x at regular intervals of x. If we do that, then we can define each interval as one side length of a quadrilateral that covers a specific area. For instance, if we use the trapezoidal rule, we can form trapezoids that, in sum, approximate the total area under the curve. Naturally, the more quadrilaterals we use, i.e. the smaller the interval, the more accurate our approximation becomes. In the simplest case, we can replace the trapezoids with rectangles. If we do this, we need smaller intervals in order to arrive at the same precision as with trapezoids, but the overall procedure gets simpler because the area of such a rectangle is simply the length of the interval times the outputs of f of x that we observe at each sampled location. From here on out, we will be focusing on this simple idea of forming rectangles under the curve in order to approximate the integral. However, if we stick with our initial idea of regularly spaced samples, we soon find that this is not ideal. For one, regular sampling, especially for rendering, leads to noticeable patterns and aliasing artifacts, which is illustrated in the figure below. Another significant problem is the implied curse of dimensionality, which basically dictates that if we have a multidimensional function that we need to integrate, then the number of samples we use can only be increased in very restrictive steps. And furthermore, we face the underlying problem that with each new dimension in which we want to sample, we are basically facing exponential growth. And this is particularly problematic since, as we will see, the core solution for rendering involves an infinite dimensional integral. And just to remind you how devastating exponential growth is, let us quickly visualize the process of taking 12 samples in 1, 2, and 3 dimensions. For one dimension, 12 regularly spaced samples are not an issue at all. With 2 dimensions, we are slowly approaching the area where it starts getting problematic. And when we enter 3 dimensions, we see that this kind of growth is something that we cannot easily support. If we try to optimize the initial approach with regularly spaced samples, there are 2 observations that we can make. First, the order in which we take samples does not matter, because what we are looking for is only the sum of rectangular areas under the curve. Second, we can switch the fixed interval with something that we expect to be close to a fixed interval. And this is exactly the case for a uniform random variable. If you distribute samples uniformly in a domain, then some of them may clump together or have great distances between them. However, in general, and especially with higher numbers of uniform samples, their distribution is, as the name suggests, uniform. Hence, the distances between samples will be similar and approaching something like a regular interval. So the main change in Monte Carlo integration is the replacement of regular samples in a fixed order with unordered samples from a uniform random variable. And this has the added benefit that randomness alleviates aliasing problems and pattern artifacts. Here we see the Monte Carlo integration procedure with sample positions drawn from a uniformly distributed random variable. Other than removing the irregular samples, the rest of the procedure stays the same. In order to compute an approximation of the area under the curve, we sum up the individual values that we get for f of x at the drawn sample positions, multiply by the volume of the domain, and divide by the total number of samples taken. So again, we can see each sampling location as represented by a rectangle with one side length defined by the domain volume over n and the other by the value of f of x at the sampled location. The last step to arrive at the fully formed Monte Carlo integration procedure is to realize that we are not restricted to uniformly distributed random variables. Instead, we can use any random variable for which we know the corresponding PDF. For this general approach, we change the Monte Carlo estimator slightly. Instead of multiplying the sum of sampled function values by the domain volume, we now divide each sampled function value by the PDF at the sample location. Now remember that we can interpret the PDF in 2 different ways. For one, we can see it as a relative indicator for how likely it is that a specific sample location is picked. That means that if a particular portion of the curve is sampled frequently, the reciprocal of the PDF gives such samples a lower weight. Alternatively, remember that we can interpret the reciprocal of the PDF as the volume of a hypercube at the corresponding point in the domain. Hence, for each sampling location, we have a computation that is similar to the one used before for uniform samples, but the factor that represents domain volume now adapts according to the PDF at the sample location, which makes perfect sense. In order to let this really sink in, we explored the rationale behind the factor 1 over the PDF of x a little more. Consider a constant function, f of x, that we are trying to integrate. In practice, this would be unnecessary, but it lets us illustrate a certain point. Now, if we sample f of x with the non-uniform PDF on the right, we find that several samples clump together at the center of the x-axis. If we apply the appropriate weighting with 1 over p of x, we see that blue samples at the center have low contribution to the final integral, while the rare red samples towards the limits have a higher contribution. This should make sense because the red sample locations are rarely sampled and thus their samples represent a larger portion of the area under the curve. The problem of ignoring this fact becomes clear when the function we are trying to integrate itself is not uniform. In this particular case here, the function f of x is actually identical to the PDF. Now if we were to give the same weight to every sample that we take, we would get a wrong result because the majority of the samples are clustered in one location. And this leads us to overestimate the area under the curve. The correct solution includes the appropriate weighting of samples by the factor of 1 over p of x. For the sake of completeness, we also provide a formal verification that the estimated value of Monte Carlo integration is in fact the integral. We use the fact that expected values of sums are equal to sums of corresponding expected values, and that constants can be moved out of an expected value. Finally, the expected value for an event of a random variable is equal to the expected value of the variable itself. Thus we can insert the continuous formulation for the expected value of x and find that, in fact, we arrive at the integral of f of x. Now we know that we can use arbitrary PDFs for Monte Carlo integration, but that does not answer the question why we would do so. However, there is a perfectly good reason for it that becomes highly relevant when we apply it in computer graphics. The concept of choosing a proper PDF for the function we're integrating is called importance sampling. The intuitive justification behind importance sampling is the following. If we can distribute more samples to those parts of the curve that we expect higher values in, we are more likely to catch fine details that have a significant impact on the final integral. We can also give analytical reasoning behind the use of importance sampling. Let us look at the variance of the Monte Carlo estimator. The estimator is a function that is based on the input from random variables, hence the estimator itself is a random variable. In rendering, the variance or the expected error that we get shows up as random noise in our output images. Looking at its contributing factors, we see that the variance of the Monte Carlo estimator depends on the number of samples and f of x over p of x. We can also see that if f of x over p of x is a constant, then the factors of the variance cancel out and there's no error and no noise. So what function should we ideally choose for the PDF to minimize noise? The short answer is a function that we can easily sample and whose shape is as close to the expected function f of x as possible. Now ideally, we could simply set p of x is f of x and variance would be completely eradicated. However, remember that what we set out to do was to actually compute the integral of f of x, and in order to generate a valid PDF, it must be normalized, which requires that we know the integral of f of x, and now we have arrived at circular reasoning. So our best bet is to find a good fit for the approximate shape of the sampled function f of x in the general case. And there are some not too complicated candidates which we will explore in detail next time. For now, let's just look at an example of noise in rendering and the effect of importance sampling. At the top, you see a model that indicates from which directions the most light is reflected at a point in space. The arrows indicate that the light function is sampled uniformly in all directions, hence we get an unoptimized output picture with lots of noise. In contrast, for the lower picture, an importance sampling strategy is used. You can clearly see that most of the sample directions are close to the one from which most of the reflected light arrives. As a consequence, the variance is noticeably reduced and the output image contains significantly less noise. Finally, we can bring together all the individual steps that we saw today into a routine for Monte Carlo integration. A minimal implementation of this procedure could look something like the code given below. Given a function to integrate, f of x, a desired PDF for a random variable, as well as its CDF, we can compute the Monte Carlo integral with a given number of samples by drawing them from a canonical random variable, converting them to sample locations according to the variable's PDF by applying the inverse CDF, and summing the output values of f of x at the corresponding locations appropriately weighted by the reciprocal of the PDF at location x. With this, we conclude the first part of the Monte Carlo integration lecture and hope that we were able to give you a hint of its usefulness, underlying concepts, and overall elegance. We also hope to see you again in the upcoming parts.